This is the Unit 8 practice test. So I'm doing pages 1 and 2. I like to separate the videos so they're not too long. And also I didn't do pages 3 and 4 just yet. I literally do these on the bus. Yeah, I didn't have time. But yeah, let's just get into it. First problem, we have this spring and then this kid is going to kick it with a certain speed of 4 meters per second. So we want to figure out what is the amplitude, because as a result of that, what's the amplitude of the oscillations? So yeah, this is just a conservation of energy problem. We know that the energy initial is going to equal the energy final because there's no outside forces doing work. And specifically, we know that the initial energy is all kinetic energy. And then when it's reached its amplitude, it's not going to be moving, it's all going to be used spring. So I'm going to actually do this as a derivation. I like to do this a lot. If you need derivation practice, just turn every math problem to a derivation, right? Because then you can just solve at the end and plug in everything you know. So I know k is 1/2 mv squared, and then it's going to be 1/2 kx squared. And then we're going to get rid of the half, right? We multiply 2 by both sides. So we have mv squared equals kx squared. And we're solving for x, so we'll just divide by k on both sides here. So we have m over k v squared equals x squared. M over k, we've seen that in the period of a pendulum. I don't think it really means anything here. I'm just doing this because then when we square root, we can cancel out the v here. So we get v squared, right? So we can get v m over k equals x. So then you just plug in your v, which is 4 meters per second. Plug in your mass, which is, 3 kilograms. Plug in your k, which is 450 newtons over meters, and you'll get an x, or a stretch, of 32.7 centimeters, so 0.327. I can't actually read my handwriting, but yeah, I'm guessing that's what it is. Calculate the frequency of the resulting oscillations. So you didn't even need to do this step to do this, right? Because we know that frequency is 1 over t, so we just solve for t and then do 1 divided by that. So t spring is 2 pi square root m over k. You can plug that in, right? You have all your values. Mass is 450, whatever, right? You can plug that all in. And then just whatever you get, take the inverse of that, or not inverse, but yeah, reciprocal? Yeah, reciprocal of that. I got 41.3 hertz. Maybe that's wrong, let me know. I'm too lazy to, I didn't have my TIE4, so I'm not gonna just go through on the, my phone. But yeah, I think I should be right. Hopefully that's right, unless I mess something up. If the kid kicked it, starting from rest again, even harder, so the velocity tripled, then what's going to happen to the amplitude change? So this is where actually sort of deriving an equation is nice, because we saw that, okay, let me erase all this. We derived this equation, and we saw that, hey, v square root m over k is going to equal x. So if we make the v 3 times as much, our x is going to be 3 times as much. So it's going to be, whatever 3 times 32.7 is. And even if you don't derive an equation, we just use the good old proportional reasoning. We can do v squared, so, if we did 1/2 m 3v squared, 1/2 k something x squared, right? We know that the squared is going to become 9 times more, but then this is going to be 9 times more, but there's also the square here, right? So we're going to have another 3, and everything will balance out. So yeah, both ways work. I think on a test you can actually do this method if you prefer that. I don't know. You'd have to ask your teacher if you can derive and then do it. By what factor should the frequency change? There's no change. We know this. There's no amplitude inside the period equation. The only thing kicking it harder did was change the amplitude, but the amplitude is not an equation. So there you go. All right, let's do the graphs. We've done this kind of a million times at this point, but they're good practice. If you're taking calculus, these should be a breeze. Really, I don't know. I would still encourage to think it through. Okay, position. I forgot to draw these out beforehand. Position versus time. It actually starts at equilibrium, so don't memorize that position versus time is, always cosine. In this case, it's not going to be cosine. The position was initially 0, right? It's at equilibrium. But then when the kid kicks it in the to the left, the position is going to get negative. And then we're going to see that oscillation, right? It's going to go back and then, forth again. Cool. Velocity versus time. We're just graphing slope. We've done this a million times. So initially the velocity is negative. Then it becomes 0. And then it becomes positive. And then it becomes 0. And then it becomes negative. I'm going faster with these, but hopefully you can see that this is no different than what we've been doing. Acceleration versus time. Initially, there's no acceleration. There's no slope. And you can even see that here, like for that one instant, the slope isn't going to change. That's a bit more second derivative stuff. Don't worry about that. But hopefully you can see that the slope here is, 0. So this becomes a positive slope. 0 slope, negative slope, 0 slope. Okay. Let's do F spring now. So there's a kind of few ways you can do this, or at least think about this, if you want a shortcut way. But once again, thinking through it will also get you to the right answer. If you think through it, initially, that's actually, okay, if you think through it, initially there's no force spring, but it's going to move a lot. It's moving very fast, so it's going to gain a lot of force spring, and then at the very, amplitude, it's going to have, it's not going to have moved much. There's not going to be much change in force spring, and then you can kind of, figure out your force spring graph. But let's say you couldn't think through it. Let's say you're in a pinch. You can't really think through why is it going to be a sine graph, right? Why can't it be something like this? Like why did it have to be sine? And just remember, there's two equations you can use. Force spring is equal to negative kx. So we know force spring and position are directly related, and they're opposites. So if the x goes negative, the force spring is going to go positive by the same amount. Well, not the same amount, but it's proportional, right? And then as the x starts going positive, the force spring starts going negative. You can also connect it back to F equals ma. So we know the F net is force spring, so it's going to equal ma, right? The S is our F net equation. So now the force spring and the acceleration are directly proportional, and that's why the graphs match. That's just another way to sort of think about it. We can go over to kinetic and elastic energy now. Yeah, we can do it like this. Okay, kinetic, U spring, TME. T. Okay, so total mechanical energy is a straight line. It's conserved. Energy is conserved at least. The kinetic energy, initially it actually starts with kinetic energy. This is not the case where it starts stretched. It actually starts moving. So we can draw a little point here. At the sort of quarter mark, when it reaches its first amplitude, it's going to look like that. And then at its next amplitude, at its equilibrium, it's going to have all of its k back. And then the next amplitude is going to have 0k because it's not moving, and you'll get a graph sort of like this. Not perfect. I didn't, reach those points, but yeah. There you go. Hopefully that kind of makes sense, right? Because there's not stretch, stretch, not stretch, stretch, not stretch. Same thing. Now, elastic energy is just kind of the quote-unquote opposite of that. It's like right? Because, everything is going to be constant. So when there's all k, there's 0 U spring. No k, all U spring. And then you'll get your graph that looks kind of wonky for me, but should hopefully look like that. So those are the graphs. I sort of explained maybe a little bit too much. How much time? 9 minutes, not bad. Sorry for explaining too much, but I just hopefully, if anyone was confused on them, now they can actually understand it, because I think this will be kind of a big thing on the test. So, I should never erased it. Okay, while I'm explaining, I'm going to redraw it because I actually need these graphs again. So looking at your kinematics graph, right, because we had this graph. Looking at the kinematics graph, we need to figure out, we're going to have this explanation, what is a time where the velocity is increasing but the acceleration is decreasing? What time did you pick? And we're going to explain, like, what does that even mean? How is that possible? Okay, so this kind of made me think for a second. Hopefully it did for everyone. We know that, so they want us, when is the velocity increasing and when is the acceleration decreasing? So I kind of took that as, when is the velocity getting bigger? Like, when is the sort of magnitude getting bigger, and when is the magnitude of acceleration getting smaller? So right here is where the acceleration is 0, right? And then this interval, or okay, wait, from this interval and this interval, the speed or the velocity is getting bigger, right? Because it's moving away from the t-axis, because that was kind of a kinematics thing, right? Because if this is 0, if it's getting away from it, the speed is getting bigger. It's moving faster and faster. And in contrast, right here and sort of right here is when it's getting close to the zero or the t-axis. This is when the acceleration is getting smaller. It's not accelerating as much. So if you look at our interval, there's kind of 2 times. You could pick right here or right here. I'm going to just pick right here. Now, and then if we like sort of correspond everything, that would be right here. What does this even mean? Like, what does that even mean if the acceleration is getting smaller and velocity is getting bigger? So, I mean, acceleration kind of, I don't know if I'd say cause, but it sort of, leads to a change in velocity, right? A is equal to change in v times time. So, right? It's equal to v over time, yeah. And so if acceleration is causing a change in velocity, if your acceleration is decreasing, that just means your velocity isn't changing as much. Instead, what's happening is your velocity is not changing as much. So if your velocity is getting bigger, but your acceleration is getting smaller, your speed is building, but then your velocity slowly is not changing as much. It's kind of hard for me to explain. It's actually the first time I really got a problem like this, but like if you think about a car, right? Think about a car that you put your gas on. So initially you're accelerating, right? But then as you're getting faster and faster and faster, you're slowly letting off the gas. You're not braking. You're just slowly letting off the gas. What's happening is you're getting faster and faster, but then when you're taking off the gas, you're just not speeding up as much, right? You slowly let off the gas. That's really what's going on here. So in this moment, this is when it's going to equilibrium, because this is right here, equilibrium. So as it's approaching equilibrium, it's getting faster and faster, but its velocity is slowly not changing as much. So yeah, pretty interesting explanation there. Hopefully that kind of made sense with my car analogy. Students are conducting an experiment with pendulums in the classroom. Okay, so this is kind of in some groups are like changing their mass, some groups are changing their length, some are changing their length and amplitude. Yeah, okay. So group A, so there's group A and B. Group B has made their string 4 times longer. So what factor would you expect the period to compare? For group B, like how much will it be compared to group A? This is just proportional reasoning. We know that, and I'm gonna switch things up. I'm just gonna do T pendulum squared equals 4 pi squared over G times L. And I kind of, or I'll do like lowercase l so people don't confuse it for angular momentum. This just comes from me squaring T P equals 2 pi square root L over G. This is the exact same equation, okay? I'm just squaring it to begin with. And the reason for that is because I can show you very clearly that, okay, if we do 4 pi squared over g, if we make L, what was it, 4 times bigger, then TP squared, right, the left-hand side has to get 4 times bigger. But of course there's that square, so we have to sort of put inside the parentheses. Oh my. So the period is going to get 2 times longer. Now here's the explanation for that. Explanation B. So the length, so let's draw this, right? The length is a lot bigger, but the mass stayed the same. So, and also the amplitude for that angle stayed the same. What does that mean? Well, that means that the restoring force stayed the same. The Fg, x, the restoring force is the exact same. So it's going to have the same acceleration. Because once again, same mass. So same acceleration. The distance, though, is a lot bigger. So same acceleration over a greater distance, you're going to have a longer period. So hopefully that kind of makes sense there. Now we got to do by what factor would you... So group C and D now, D has the 4 times longer, or 4 times bigger, what is it, masses? Yeah, 4 times bigger masses than group C. So by what factor would you expect group D's period to be different from group C's? Hopefully this kind of just rings in your head that, or is that how you say it? I don't know. TP is equal to 2 pi square root L over G. There is no mass in this equation. So, no mass in the equation, it's not going to affect it. Why? Like, explain why. Well, more mass means more restoring force. So if I draw my new sort of chart here, or I don't know, diagram, a bigger M means bigger Fg. So it's gonna it should accelerate more, but it has more mass, so it has more inertia. It's harder to accelerate. So it if you think about Fg equals ma, right? It balances out. The acceleration is the same amplitude and length means same distance. So it's gonna travel the same distance with the same acceleration. That's why mass does not affect period. So yeah, that was pages 1 and 2. I'll get pages 3 and 4 done, lickety split, and then I'll talk about those. So yeah, thank you for watching. Have a good day.